Okay, so in the previous lecture we began to discuss dual pairs and weak topologies. So let's recall the definition. A dual pair is a triple consisting of a pair of vector spaces x and y and a non-degenerate bilinear form of their product. So the angle brackets denote a bilinear form, which is called a pairing of x and y. And the non-degeneracy condition of this form is equivalent to the following. Since it's a bilinear form, it induces two linear maps from x to the algebraic dual of y, which is denoted, we denote the algebraic dual by this symbol, y hash. And similarly, we have a map from y to the algebraic dual of x. So both maps are induced by this bilinear form in the following way. And now the non-degeneracy condition for this bilinear form means precisely that these two maps are injective. So we'll often identify x with a subspace of the dual of y, and similarly y with the subspace of the dual of x by means of these embeddings. And a brief notation for a dual pair is the following. So a dual pair is a purely algebraic object, but we can easily make it into a functional analytic object by introducing the so-called weak topologies. So let's recall the definition. If you have a dual pair, then for each element y in the second space y, we define a seminorm on x by the following formula. And we define the weak topology of the dual pair, denoted by sigma of xy, to be the locally convex topology on x, generated by all such seminorms. This is the weak topology. So x becomes a locally convex space under the weak topology, and similarly y becomes a locally convex space under the weak topology sigma of yx. We have the following two important special cases. If we have a Hausdorff locally convex space x, then we can consider two dual pairs, x and x star, where x star is now the topological dual, that is the space of all continuous linear functionals, and the dual pair x star and x. And we can consider the respective weak topologies on x and on x star. So the weak topology on x determined by x star is denoted like this, and it's called the weak topology. And the weak topology on x star determined by x is denoted like this, and it's called the weak star topology. Weak star topology on x star. Okay, let's now discuss some properties of these topologies. So suppose that we have a dual pair, x and y. And let's denote x equipped with the respective weak topology simply by x sigma. So our first goal will be to identify the topological dual of x. or equivalent to describe all continuous linear functionals on X continuous with respect to the weak topology. First of all, let's observe the following. If I take an element in Y, so we follow this convention and interpret Y as a linear functional on X, so we have the following qualities. Y of X is X and Y, and this is the semi-norm of X determined by Y. So these equalities imply that Y is continuous. Y is continuous with respect to the weak topology. So indeed, let's recall that if in a general case, if we have a locally convex space X and a generating family of semi-norms on X and a linear functional on X, then this functional is continuous with respect to the topology determined by this family, if and only if its absolute value is dominated by finitely many semi-norms from our family. Here, this condition is obviously satisfied. In fact, we have an exact equality, and so Y is continuous. So this follows from our general criterion of continuity for linear functionals. Okay, so we conclude that Y is contained in the dual of X sigma. I claim that, in fact, these spaces are the same. So we have the following proposition. To prove this result, we need a simple algebraic lemma. Suppose that X is a vector space, and suppose that we have finitely many linear functionals on X. Let's denote them by F1, Fn, and just F. Linear functionals on X. Then the following conditions are equivalent. Condition 1, the kernel of F contains the intersection of the kernels of the functionals F1 to Fn. And condition 2, F is a linear combination of the functionals F1 to Fn. The proof is a simple exercise in linear algebra. Of course, it's clear that 2 implies 1. If F is a linear combination of these functionals, then we have this inclusion. But the converse is also true, and it's quite easy to show by considering suitable quotients of X. By the way, implicitly this lemma appears in the standard calculus course when you discuss Lagrange multipliers. Okay, let's now apply this lemma to our proposition. So we already know that Y is contained in the dual of X sigma. So we have to prove the opposite inclusion. So we take a functional F, a continuous functional on X sigma, and we apply our general criterion of continuity for linear functionals. So this criterion implies that there exists a positive constant C, and there exist finitely many semi-norms from the generating family, or equivalently finitely many semi-norms of this form. So there are finitely many vectors y1 to yn, such that f of x is dominated by the following maximum. Okay, let's now recall the definition of these semi-norms. So here's the definition. And so after we identify y I with linear functionals on x, we can write this in the following way. But now we observe that this function, this inequality easily implies that the kernel of f contains the intersection of the kernels of the functionals y1 to yn. So if this is 0 for some x, then this is also 0. So we have this inclusion, and our lemma implies that f is a linear combination of the functionals y1 to yn. And this is, of course, contained in y. And this completes the proof. So we have shown that each continuous linear functional on x sigma sits in y. Okay, let's now look at some corollaries. Corollary 1. Suppose that x is a Hausdorff locally convex space. So in this case, again, we can consider these dual pairs, this one and this one, and we get the following. If we equip x with a weak topology, then the dual will be the same as before. I mean that if we equip x with the original topology, or if we equip x with a weak topology, but the duals are the same. By the way, let me recall that the weak topology on x is usually weaker than the original topology. And in most interesting cases, it is strictly weaker. But nevertheless, the space of continuous linear functionals is still the same. And dually, if we take x star and equip it with the weak star topology, then the dual of this space will be just x. Or more exactly, will be canonically isomorphic to x by means of those embeddings. Okay, let's now consider a special case where x is a normed space. This is corollary 2. Suppose that x is a normed space. So we know that in this case, the dual of x is also a normed space with respect to the canonical norm. And so we have at least 3 natural topologies on the dual. The usual norm topology generated by the norm, the weak topology, because the dual is a locally convex space, and the weak star topology, because the dual is dual to x. And so we have the following relation between these topologies. So the weak star topology is weaker than the weak topology, and the weak topology is weaker than the norm topology. On x star. And part 2, natural question is when some of these topologies are the same. And here's the partial answer. The weak star topology equals the weak topology on x, if and only if x is reflexive. So this is a new reflexivity criterion for a normed space. Well, to prove the first result, we actually need to show only this inclusion, because we have already observed at the previous lecture that for an arbitrary locally convex space, the weak topology is weaker than the original topology. So we consider the canonical embedding of x into the bidual. Let's denote it just by I. the canonical embedding into the bidual. So we observe now that for each x in X and for each f in the dual, the seminorm on X star, so one of the seminorms which generates the weak star topology can be written as follows. So f of x is I of x applied to f, but this is also one of the seminorms which generates the weak topology on X. So we have the following inclusion. The family of seminorms on X star that generates the weak star topology. So this family generates the weak star topology. Is contained in the family of seminorms that generates the weak topology. So these seminorms are indexed by elements of the bidual. So this family is contained in this family by means of these equalities. And so this implies, of course, that this topology is weaker than this topology. Let's now prove the second statement. Well, the right to left implication. The right to left implication also follows from this inclusion. So if X is reflexive, then all seminorms from this family are of this form. So these families are the same, and so the topologies are also the same. And to prove the left to right implication, we do the following. So we assume that these two topologies are the same, and we look at the bidual of X, X double star, and we apply corollary 1. By corollary 1, this can be written as follows. We replace the norm topology on X star by the weak topology, but the dual is still the same. Well, now we use our assumption. We replace now the weak topology by the weak star topology. And again, we apply corollary 1. So by corollary 1, this is canonically isomorphic to X by means of the canonical embedding. But this means exactly that X is reflexive. Okay. Let's now discuss a general notion of dual operator between spaces of the dual pair. Suppose we have two dual pairs, x1, y1, and x2, y2. Two dual pairs. And we give the following definition. Suppose that we have two linear operators, T, which acts from x1 to x2, and S, acting from y2 to y1. So we say that such operators are dual to each other. They are dual to each other if the following identity holds. The pairing of Tx and y equals the pairing of x and sy for all x in x1 and for all y in y2. Okay, so this is formal definition. So formally, linear operators T and S form a pair. But actually, let's now observe that T uniquely determines S, and S uniquely determines T. Namely, this follows again from our embeddings of y1 into the dual of x1 and y2 into the dual of x2. Indeed, if we have a linear operator, so suppose that T is a linear operator from x1 to x2, and let's consider the algebraic dual T hash, which acts from x2 hash to x1 hash by the following formula. It takes f to f composed with T. So this is the algebraic dual operator. Then there exists an operator S, which is dual to T in this sense. There exists a linear operator S, which is dual to T, if and only if T hash takes y2 to y1. So y2 is a subspace here, y1 is a subspace here. So in general, there is no reason to expect that this inclusion holds. But if it holds, then S exists. And actually, S is nothing but the restriction of T hash to y2. So in this case, S is the restriction of the dual operator to y2. So this is immediate from this formula. So this is the left-hand side is y applied to T applied to x, and the right-hand side is S of y applied to x. So S is nothing but T hash of y. So this is a criterion for the existence of S. Let's now give a topological criterion for the existence of S. So we have the following proposition. So as before, we suppose that T is a linear operator from x1 to x2. Then the following conditions are equivalent. Condition 1, T is continuous with respect to the weak topologies on x1 and x2 respectively. Condition 2, there exists a dual operator. Dual to x, a dual to T. And condition 3, there exists a dual operator and moreover, this dual operator is continuous for the weak topologies on y2 and y1. So this is a topological criterion for the existence of a dual operator. S exists if and only if T is continuous with respect to the weak topologies. Okay, so first we show that 1 and 2 are equivalent. Again, we call our basic criterion of continuity for linear operators between locally convex spaces. This criterion states that T is continuous if and only for each semi-norm on x2, which belongs to the generating family on x2, the composition of the semi-norm with t is continuous on x1. So in our case, this means that for each y in y2, the function which takes each element from x to the following number is continuous. On x1 with respect to the weak topology. Okay, let's now look what it is. So this is the pairing of tx and y, or equivalently this is y applied to t of x. Y applied to t of x. So this function should be continuous, but this guy is a linear functional on x. So we now apply our previous result. Where is it? It was on that board. Okay, so the result was that a linear function on x1 is continuous with respect to weak topology, if and only if it belongs to y1. Let's also recall that a linear functional is continuous, if and only if its absolute value is continuous. So this means that for each y in y2, y composed with t is continuous on this space, but we know that this means exactly that it sits in y1. But this is nothing but t hash applied to y. So we see that this condition means exactly that t hash takes y2 to y1. And we already observed that this condition is equivalent to the existence of the dual operator. So we conclude that 1 and 2 are equivalent. 1 and 2 are equivalent. Okay, now it's clear that 3 implies 2. This is obvious. And to show that 2 implies 3, we observe that if S exists, then of course T is the dual of S. So S has a dual. But we already know that 1 and 2 are equivalent. So we simply apply the equivalence between y and 2 to the operator S. So T is the dual of S. And since 1 and 2 are equivalent, we already know that 1 and 2 are equivalent, we conclude that S should be continuous for the weak topologies. And that's it. So we see that 2 and 3 are actually equivalent. Here is a useful corollary. Suppose now that x and y are Hausdorff locally convex spaces, and T is a linear operator from x to y. let's consider the following conditions. Condition 1, t is continuous. Condition 2, t is continuous for the weak topologies. Condition 3, there exists a dual operator t star from y star to x star given by the following formula. And condition 4, there exists a dual operator t star and this operator is continuous with respect to the weak star topologies. With respect to the weak star topologies on the respective spaces, y star and x star. I claim that in the general case, 1 implies 2, and 2, 3, and 4 are equivalent. That's only we can say in the general case. But in some cases, all these statements are equivalent. For example, if x and y are normed spaces, if x and y are normed spaces, then all conditions are equivalent. Well, first of all, let's observe that 1 always implies 3. This is clear because if t is continuous, then for each continuous linear functional f on y, this composition is a continuous linear functional on x, and so we get a well-defined operator t star. So clearly 1 implies 3. And now we apply our previous result, which implies that 2, 3, and 4 are equivalent. This follows from the previous proposition. So let's now assume that x and y are normed spaces, and let's show that all the four conditions are equivalent. Suppose that x and y are normed spaces. And let's show that 3 implies 1. 3 implies 1. So we suppose that t star exists, and we want to show that t is continuous, or equivalently that t is bounded. In other words, we want to show that the image of the closed unit ball is bounded in Y, where bold B is the closed unit ball of X. And let's now recall the Banach-Steinhaus theorem. So this is a subspace of Y, and we know that a subspace of a normed space is bounded if and only if all continuous linear functionals may map this set to a bounded set of the base field. So by the Bernstein-Haus theorem, this means exactly that for each f in y star, f takes this hypothetically bounded set to a bounded subset of the base field. So we have to now prove that this condition holds. But this condition holds because this is nothing but T star of f applied to B1. And by assumption, T star of f is a bounded linear functional on X. So since it is bounded, this is also bounded. So this is true because T star of f is a bounded functional on X. And this completes the proof. So we see that the proof is short, but it involves a strong increment, namely the Bernstein-Haus theorem. Here's a useful exercise. First of all, the assumption that x and y are norm spaces can be generalized. Let it be part A. So conditions 1, 2, 3, and 4 are equivalent if and okay, so they are equivalent, and here we have two exercises. Exercise A, they are equivalent if X is the norm space and Y is an arbitrary Hausdorff locally convex space. Actually, not necessarily Hausdorff. Y is any locally convex space. But this can also be generalized. This is exercise B, which is a bit harder. These conditions are equivalent if X is metrizable. X is a metrizable locally convex space, and Y is any locally convex space. But in the general case, this is also an exercise. In the general case, conditions 1, 2, 3, and 4 are not equivalent. This last statement is contained in our next exercise sheet. Number three. Number 4 will be about spectral theory in Hilbert space. So exercise sheet 3 is about topological vector spaces. Okay. Our next goal will be to discuss annihilators in a general setting of dual pairs. So we have already discussed annihilators in the context of norm spaces at the end of the previous term and at the beginning of this term. And so now extend this notion to arbitrary dual pairs. So suppose that we have a dual pair of vector spaces, X and Y. And suppose that M is a subset of X. And we give the following definition. we define the annihilator of M with respect to our dual pair in the following way. So the annihilator is a subset in Y, denoted like this. Or simply like this when we suppose that our dual pair is fixed. And it consists of all elements in Y such that xy is 0 for all x in M. Here are two special cases of this notion. Suppose that X is a Hausdorff locally convex space. So we define the annihilator of a subset in X to be the annihilator of a set with respect to the standard pairing between X and X star. So this is the collection of all continuous linear functionals on X that annihilate M. And dually, we define the pre-annihilator of a subset M in the dual to be the annihilator of N with respect to the dual pair X star X. So we have already met these notions in the context of normed spaces, but actually they make sense for any Hausdorff locally convex space and more generally for any dual pair of vector spaces. In Russian, annihilator is annullator. And pre-annihilator is predannullator. Yeah, because we take the dual pair X star and X, so the pre-annihilator sits in X. And this sits in X star. Let's look at some simple general properties of annihilators. We have the following proposition. Suppose that X and Y is a dual pair. Then, if you take the 0 subspace in X, then the annihilator is Y. And the annihilator of X is 0. This is clear, and this follows from the fact that the pairing is non-degenerate. Condition 2, also trivial. If M1 is contained in M2, then the annihilator of M2 is contained in the annihilator of M1. This readily follows from the definition. Condition 3, for each subset M in X, the annihilator of M is not just a set, but is actually a weakly closed vector subspace. Of Y. And property 4, if we again start with an arbitrary subset of X, then the annihilator of M equals the annihilator of the weakly closed linear span. So this notation means that we take the weak closure of the linear span in X, and then take the annihilator. Well, 1 and 2 are trivial. 3 and 4 are almost trivial, because 3 follows from the fact that, so we can write the annihilator in the following way. We interpret each element of X as a linear functional on Y. And by the definition of the annihilator, we can write the following equality. But we already know that each element in X is a continuous linear functional on Y. Each X is a continuous with respect to the weak topology, linear functional. And of course, the kernel of a continuous linear functional is a closed vector subspace. And the intersection of any family of closed vector subspaces is a closed vector subspace. And similarly, property 4 follows from the fact that each Y is a weakly continuous linear functional on X. So if it vanishes on M, then by linearity it vanishes on the linear span, and by continuity it vanishes on the closure of the linear span. Okay, we now introduce the double annihilator. By definition, the double annihilator of a subset M in X is the following. First, we take the annihilator, and we get a subspace in Y. And again, we take the annihilator once again with respect to the dual pair Yx, and we come back to X. So briefly, this will be denoted by the following formula. So this is a subset in X. In Russian, двойной аннулятор. A simple corollary from the previous proposition is that if we take the linear span of M and take the weak closure of the linear span, then this is contained in the double annihilator. Well, indeed, this follows from the previous proposition because M is clearly contained in the double annihilator. But since the right-hand side is a weakly closed linear subspace, we take the closure of the linear span, and we still have the inclusion. I claim that, in fact, these subspaces are the same. So we have the following theorem. Theorem 1. This is the double annihilator theorem for dual pairs. So if we have an arbitrary dual pair, X and Y, then for each subset M in X, the double annihilator of M equals the weak closure of the linear span of M. And before we prove this result, let's state a similar result for locally convex spaces. Theorem 2, this is the double annihilator theorem for locally convex spaces. Suppose that X is a Hausdorff locally convex space. I claim that for each subset M of X, the double annihilator, so, or equivalently the pre-annihilator of the annihilator of M, is the closure of the linear span, where the closure is taken with respect to the original topology on X. Closure with respect to the original topology. So this is not a special case of theorem 1, because we take not the weak closure, but the closure with respect to the original topology. And actually, we will see now that theorem 1 follows from theorem 2. So first of all, let's prove theorem 2. Okay, so let's take the linear span, the closure of the linear span, and let's denote it by x0. X0 is the closure of the linear span of M. Well, it's clear that in this case, the annihilator of M equals the annihilator of x0. Again, if a continuous linear functional vanishes on M, then it vanishes on the closure of the linear span. And so the double annihilator of M equals the double annihilator of x0. So now to prove theorem 2, it suffices to show that x0 equals the double annihilator of x0. So we want to show that x0 equals the double annihilator of x0. Well, clearly we have the inclusion. This subspace is contained in here. And conversely, suppose that we have a linear function, we have a vector. Suppose that X is an element in X, which is not in X0. We know that in this case, X and X0 can be separated by a linear functional in the following sense. There exists a continuous linear functional on X such that f vanishes at x0, but doesn't vanish at x. So this result was proved at the previous lecture. Okay, so this means that f sits in the annihilator of x0. And since f doesn't vanish at little x, we conclude that x doesn't belong to the annihilator of f. More exactly, to the pre-annihilator of f. And moreover, this implies that x doesn't belong to the pre-annihilator of the annihilator of x0. And that's it. So we have shown that if X is not here, then it is not here. So these two subspaces are the same. Okay, so this completes the proof of theorem 2. So we see that actually theorem 2 is essentially equivalent to this statement, to the statement that closed vector subspaces and linear and vectors, which doesn't belong to the subspaces, can be separated by linear functionals. Now, to prove theorem 1, we simply apply theorem 2 to X equipped with the weak topology. So we know that in this case, the dual of X becomes Y, and the theorem 1 becomes a special case of theorem 2. Okay, let's now look at some corollaries of the double annihilator theorem. Corollary 1. Suppose that X is a Hausdorff locally convex space. And X0 is a vector subspace of X. I claim that, yeah? Yeah, X is Hausdorff. We observed this in the previous lecture. If I have a dual pair, X and Y, and equip X with the weak topology, then X is Hausdorff because continuous seminorms, the generating family of seminorms separates the points. If we have a non-zero vector in X, then we can always find a non-zero an element in Y, which doesn't vanish at X. And this means that the respective seminorm doesn't vanish on this vector. But this is equivalent to the property that X is Hausdorff. So the weak topology of the dual pair is always Hausdorff. And so theorem 1 follows from theorem 2. Okay, so now we take a Hausdorff locally convex space and a vector subspace of X. I claim that the closure of X0 equals the weak closure. And in particular, X0 is closed, even only if it is weakly closed. Well, this is not entirely trivial because we know that in a general case, a weak topology is strictly weaker than the original topology. So in general, we can find many subsets in X0 which are closed, but which are not weakly closed. But for vector subspaces, this is equivalent. And the proof is immediate from theorems 1 and 2, because by theorem 1, the weak closure of X0 is the double annihilator. But by theorem 2, the closure of X0 is also the double annihilator. And that's it. By the way, this result can be extended to arbitrary convex subsets of X. So it turns out that a convex subset of X is closed even only if it is weakly closed. But this is a little bit less trivial, so we skip this result. Okay, corollary 2. Suppose that X is a Hausdorff locally convex space. Suppose that M is a subset in X, and N is a subset in the dual. So part 1. So first of all, we write again the double annihilator theorem, which states that the closure of the linear which states that the double annihilator of M is equal to the closure of the linear span of M. If we now combine this with corollary 1, we see that this is the same as the weak closure of the linear span. Part 2, so if we start with a subset in the dual, then the annihilator of the pre-annihilator is equal to the weak star closure of the linear span. Again, this is a special case of the double annihilator theorem. In the special case where X is a normed space, we can continue this equality. So if X is a normed space, then we have the following chain. So the double annihilator of N, or more exactly the annihilator of the pre-annihilator, equals the weak star closure of the linear span. This subspace contains the weak closure of the linear span. And this is the same as the norm closure. Well, again, this equality is a special case of corollary 1. And this inclusion follows from the fact that in the general case, the weak star topology is strictly weaker than the weak topology. And in the general case, this inclusion can be proper. But in the special case where X is reflexive, this is part 4, if X is a reflexive Banach space, then we know that the weak star topology and the weak topology on the dual are the same. And so all the spaces in this chain are the same. All spaces in this chain, let's denote it star, are the same. But if X is not reflexive, that it can happen that this inclusion is proper. Excuse me? Yeah, reflexive normed space is always a Banach space because the double dual, the bidual, is complete. So if the inclusion of X into the bidual is an isomorphism, then X has to be complete because X double star is always complete. Corollary 3. Corollary 3 is a useful density criterion for a vector subspace. So first of all, we state it for dual pairs. Suppose that X and Y is a dual pair of vector spaces, and X0 is a vector subspace in X. I claim that X0 is dense with respect to the weak topology. X0 is weakly dense in X, even only if its annihilator is 0. This is also immediate from the double annihilator theorem. So it's clear that if X0 is dense, then the annihilator is 0, because the annihilator equals the annihilator of the closure. And the reverse implication follows from the double annihilator theorem, because if this is 0, we take the pre-annihilators, And we see that the double annihilator of x0 is x, but the double annihilator is the closure. So we conclude that x0 is dense in X. Corollary 4. Suppose now that we have a Hausdorff locally convex space. X0 is a vector subspace in X, and Y0 is a vector subspace in X star in the dual. Then I claim that X0 is dense with respect to the original topology, even only if it is weakly dense, even only if the annihilator is 0. So this follows from the previous proposition, from the previous corollary, and this is also true because of corollary 1. So the weak closure and the closure are the same. And dually, Y0 is weak star dense in X star, if and only if the pre-annihilator is 0. Okay, corollary 5, which is a useful special case of corollary 4. Suppose that X is a normed space. Then the canonical image of X in the bidual is weakly star dense. In the bidual. By the way, if X is a Banach space, which is not reflexive, then we know that the canonical inclusion, canonical embedding is isometric. So X becomes a closed vector subspace in the bidual. And of course, it is not dense for the norm topology. But it is always weakly star dense. And this is a special case of part 2, because when we look at the canonical image of X in the bidual, we immediately see that the pre-annihilator is trivial. Because, well, if you take a linear function on X, such that all elements of this canonical image vanish on this functional, this means exactly that this functional is 0 by the definition of the canonical embedding. So we see that the pre-annihilator of X in X double star is trivial, but this means exactly that X is weakly star dense in the bidual. Okay. Another corollary of the double annihilator theorem is about linear operators. Corollary 6. Suppose that X and Y are Hausdorff locally convex spaces. And suppose that T is a continuous linear operator from X to Y. Then we have the following inequalities. First of all, the kernel of the dual operator equals the annihilator of the image of T. Second, the pre-annihilator of the kernel of T star equals the closure of the image of T, which is the same as the weak closure of the image of T. Part 3 is a dual to 1. The kernel of T equals the pre-annihilator of the image of T star. And part 4, the annihilator of the kernel of T equals the weak star closure of the image of T star. So let's recall that some time ago we proved that if X and Y are norm spaces, and if we take the norm closure of the image of T star, in general this norm closure is contained in the annihilator of the kernel. But in the general case, we didn't have an exact formula for the annihilator of the kernel. And now we have the exact formula. The annihilator of the kernel is the weak star closure of the image of T star. And in the case of norm spaces, this can be strictly bigger than the norm closure. The proof is very easy. Part 1 is almost immediate from the definition. So f sits in the kernel of T star, that is T star of f is 0, if and only if. So T star of f is f composed with T. So this should be 0 for all x in X. But this means exactly that f sits in the annihilator of the image of T. To get part 2, we simply take the pre-annihilators in part 1 and use the double annihilator theorem. So we take the annihilators and we conclude that the pre-annihilator of this equals the closure or equivalent to the weak closure of the image. And now to get 3 and 4, the easiest way to get 3 and 4 is to apply 1 and 2 to the dual operator. Apply 1 and 2 to the operator T star acting between the weak star dual spaces. So we know that the dual of T star, if we consider T star with respect to weak star topologies, then the dual of T star will be T. And so 3 and 4 readily follow from 1 and 2. Yeah, of course. Hash is the algebraic dual, but here we take the topological dual.
Or is it continuous?
Well, the star means the topological dual, the space of continuous linear functionals. So we know that if we take this space, so we take X star, the topological dual of X, we equip it with the weak star topology, and we take the dual again, of course, the topological dual, then we get X. This was, well, some result from the beginning of today's lecture. So the dual of T star, the topological dual of T star becomes T. And so after we apply 1 and 2, replace T by T star, T double star will be T. And we get this and this respectively.
I asked if the T star is, so why is it continuous? If T is just a linear function, then...
No, T is continuous. T is a continuous linear operator from X to Y. Yeah, L script is the space of continuous linear operators. Mm-hmm. Yeah. I didn't introduce any special notation for all linear operators. Maybe some time ago I denoted by home. This is the space of all linear operators from X to Y. And script L is the space of continuous linear operators. Continuous linear operators. And if Y is the base field, then we get the topological dual here and the algebraic dual. Okay, so this completes the proof of Corollary 6. And our final result for today is Corollary 7. Actually, this is a special case of Corollary 6. Corollary 7. Again, suppose that x and y are Hausdorff locally convex spaces, and T is a continuous linear operator from x to y. Then T star is injective if and only if the image of T is dense in y. And this happens if and only if this image is weakly dense in y. And we also have a dual statement. T is injective if and only if the image of T star is weakly star dense in X star. So let's recall that when we discussed norm spaces, we observed that so if X and Y are norm spaces, and if the image of T is norm dense in X star, then T is injective. But in the general case, the converse is not true. It can happen that T is injective, but the image of T star is not dense with respect to the norm topology. And now we have an exact criterion. So T is injective if and only if the image of T star is weakly star dense in X star. In the case of norm spaces, this is stronger than, this condition is stronger than the norm density of the image of T star. And this follows from our previous corollary because, well, the image of T is dense, or equivalently weakly dense, if and only if its annihilator is trivial. That is, if and only if the kernel of T star is trivial. That is, if and only if T star is injective. And similarly, this formula implies that T is injective if and only if the image of T star is weakly star dense. Okay, so that's all for today. At the beginning of the next lecture, we complete our discussion of duality by proving a fundamental theorem, which is usually referred to as the Banach-Alaoglu-Bourbaki theorem. And this theorem implies in particular that the unit ball of the dual of any norm space is weakly star compact. And after that, we finish our discussion of topological vector spaces and begin to study spectral theory of linear operators on a Hilbert space. Thank you.